Chapter 11. Decision Boundary. Let's discuss the decision boundary in logistic regression. In logistic regression, which is used for binary classification, the decision boundary is a critical concept. It is a threshold that determines how we classify a new data point based on the predicted probability. The decision boundary is the line or hyperplane that separates the space into two parts, each corresponding to one of the two possible classes, like 0 or 1 in binary classification. Logistic regression uses a logistic function to map the linear combination of features to a probability between 0 and 1. The decision boundary is defined at a point where this probability is exactly 0.5. In the logistic regression formula, the decision boundary is set where the probability of y equals 1 given x is 0.5. So, y is the threshold set to 0.5. The choice of 0.5 as the threshold is intuitive in a binary classification problem. It signifies an equal chance of the data point belonging to either class. If the probability is higher than 0.5, we predict class 1. If it is lower, we predict class 0. In real-world scenarios, getting a predicted probability of exactly 0 or 1 is rare due to the nature of the logistic function and real data. So, we classify data points with probabilities lower than the threshold as 0, and those with higher probabilities as 1. So, what if the probability is calculated to be 0.5? In that case, the data point cannot be classified in either class, but the calculated probability is really exactly equal to 0.5. Let's consider a simple logistic regression with one feature. Suppose we have a simple model which can be written in this way. The decision boundary occurs when the probability of y equals 1 given x is 0.5. As defined by the formula, this decision boundary can be expressed by this fraction. This fraction equals 0.5, so the denominator equals 2. Thus, the exponential function part equals 1. In the context of exponentiation, if e raised to the power of n equals 1, n should be 0. So, beta 0 plus beta 1 x1 equals 0, and x is minus beta 0 divided by beta 1. This equation represents how the predictor variable affects the prediction results and how the model's predictions are formed in this simple example. Let's see a 2D plot with x on the x-axis and the probability of y equals 1 given x on the y-axis. In this plot, the decision boundary is the horizontal line where the y equals 0.5. And this plot approximates the relationship between predictor x and the output. At a point where the boundary line intersects with the sigmoid line, the probability equals 0.5. So, if x is greater than this point, the probability is greater than 0.5, so the data will be predicted as class 1. If x is smaller than this point, the probability is lower than 0.5, so the data will be predicted as class 0. Consider the case where there are two predictor variables, x1 and x2. Suppose that the data are represented by this scatter plot using the values of x1 and x2. The decision boundary can be represented by this equation because the output of the logistic regression is a line of 0.5. In this case, since the denominator of the fraction is 2, the value of the exponential part of the denominator is 1. Therefore, the exponent of this exponential function is 0, and the part of this linear combination is 0. Solving this equation for x2 is represented by this equation. This equation is linear for x1 and is the equation of a line representing the change in the value of x2 with the value of x1. This equation represents the decision boundary and can be written as a straight line on the scatter plot. Let's summarize the role of decision boundary in classification. When a new data point is introduced, the logistic regression model calculates its probability of belonging to class 1. If this probability is above 0.5, the point is classified as 1. Otherwise, it's classified as 0. In cases with more than one predictor, the decision boundary becomes a surface or hyperplane in higher dimensional space. It still serves the same purpose, to separate the space into regions corresponding to different classifications.